Last time we made some remarks about Weil invariance, in particular the Young-Mills action f mu squared once it is covariantized is Weil invariant without transforming the gauge field. The Dirac action at zero mass is Weil invariant, and the transformation of psi is this one. Similarly, we have an action that's Weil invariant for the scalar field, and that is obtained by adding the non-minimal coupling r phi squared with a certain coefficient, and that is invariant once you transform phi according to a factor that tells you about its dimension. Phi has dimension 1, the fermion has dimension 3/2, and the vector has to be regarded as something of dimension 0. Then we computed the stress tensor of gauge fields by applying the usual formula, which is written here, and we found that it is traceless, and the fact that it is traceless we have connected with Weil invariance, with the fact that the action is Weil invariant, because the trace of the stress tensor is the generators with the divergence of a current that is associated with the generators of the scale transformations. Let us also write the stress tensor for a scalar field. For a Weil invariant, for a scalar field, let's say, massless, in flat space. In flat space, where we have to apply this formula to the action we have here, and possibly adding the non-minimal coupling, and then you choose the metric to be flat. Well, you understand what happens, because the derivative with respect to this just gives you two derivatives, d mu, partial mu phi, and the 1/2 is just cancelled, and the square root of g is just cancelled by that. So basically, you have t mu nu equals partial mu phi, partial nu phi, and then whatever you need to have it conserved on shell. You can find it by the formula, but you don't even need to find it from the formula, because it's uniquely fixed by the requirement that it be conserved on the solutions of the field equations. And then there is an extra term that is total derivative, if you want, one of the improvement terms that you can, let's say, always add to the stress tensor, and you can fix the coefficient, which is 1/6, to make it traceless. And that is the stress tensor that you find from this thing. How can you be sure of that? Because this first is conserved on shell, and then it is also traceless. So let's check this. If you take partial mu, here you will have box phi partial nu phi on shell. That's 0, because box phi is 0 on shell, flat space. Then you have another term, which is partial mu, partial nu phi, and you differentiate the second part. Now we have to differentiate this, which gives minus twice partial mu, partial alpha phi, partial alpha phi, and you see that these two cancel. That's what determines the relative coefficient here. So once you know the coefficient of the first term, you basically know everything else. And the last term doesn't need to be contracted with partial mu because there is a projecture there, same projecture that is originated by the scalar curvature R, and that is transverse. So that's it. So the first term is 0 on shell. Trace eta is equal to eta mu nu t mu nu, and that is, when we trace these two, we have partial alpha phi, partial alpha phi times 1. When you trace the second term, you will have 4 divided by 2, so minus 2. And then you have minus 1/6. And when you trace this object here, what you have is partial mu is a box, minus 4 box, so minus 3 box of phi squared. Which means that you have minus partial alpha phi, partial alpha phi, then you have plus 1/2, minus 3 divided by minus 6, box phi squared. What is box phi squared? That is equal to 2 phi box phi plus partial mu phi, partial mu phi. So again, you see that this vanishes on shell, the other two cancel out, and that fixes the third coefficient. So the trace is 0. What can we do with stress tensors? With stress tensors, we can determine, for example, the interaction mediated by the graviton, which is the gravitational force. So we will do it, and at the same time we will study the difference that occurs when, instead of having a graviton that's exchanged between bodies, so gravitons exchange between this and the Earth, make this pen fall to the ground. What happens if, instead of exchanging gravitons, they exchange massive gravitons? And there is a huge difference that we will show, even if the mass of the graviton is arbitrarily small. And that is called Van Dam-Veltman-Zakharov discontinuity. So basically, what do we do? Well, we know that the gravitational interaction which is what you would write like this, in case of electromagnetism, G mu A mu, is what? We found it already. It's like this. where T mu nu is the stress tensor and phi mu nu is the fluctuation of the metric around flat space. But we still don't know well what this kappa constant is, and that we will fix now by deriving the Newton potential between two bodies. So we are basically considering this diagram where you have two bodies which are described by particles of masses m1 and m2 that exchange gravitons. And this diagram is very simple because the vertex is given precisely by this thing. So the vertex has an eye because there are eyes in propagators and vertices. Probably you remember. The propagator we know what the propagator is. Let's recall what it is. Mu nu rho sigma with an impulse p, momentum p, is 1 divided by 2p squared eta nu rho eta nu sigma plus eta mu sigma eta nu rho minus eta mu nu eta rho sigma. This is the propagator we found with our gauge choice. It won't matter if we use a different propagator with a different gauge choice, but let's use this. So here we are exchanging the graviton. And okay, so let's compact this a little bit. And what will T mu nu be? T mu nu is the stress tensor, can be the stress tensor. We will compare a massive body and light. So what's the difference? Well, the difference is that in the case of light, we necessarily need a traceless stress tensor, and in the case of a massive scale or massive body, we don't, because there is certainly no Weyl invariance and no scale invariance in the presence of a mass. Well, there is a way to write the stress tensor of a point-like particle. And that is T mu nu is equal to the mass times u nu, where u mu is the fall velocity and so at rest you just have T00. So at rest, you know that u mu, the fall velocity, is 1, 0, 0, 0. And you also know that u mu is always equal to 1. So at rest, you just have T00, which is equal to the mass. And all other components are 0. So T mu nu is a mass. And then you have 0, 0, 0. That is the stress tensor of the, 2 dimensional massive particle. What is the stress tensor of light, a photon of energy E? That is quite similar. It is the energy times E mu E nu. But now E mu E nu U mu is equal to 0. And that makes this thing traceless, as it should be, because we have found that the radiation should always be traceless. But in the case of if we want to describe radiation as a quantum, like a photon in this case, this is a suitable stress tensor. So you can choose, for example, U mu equals 1, 0, 0, 1. It's like the U mu is like the momentum K mu. Next, when we want to study the potential, the attractive potential or repulsive, whatever, it will be attractive, between two bodies, we consider the static case. So why are we considering the photon? Because we will consider first the potential between two masses, and that will give the Newton law. Second, we will consider the attraction between light and a mass, and that's the deflection of light. And we will compare the massless graviton and the massive graviton. And another thing, so maybe I can better organize this by, well, whatever. Let's move on. We consider the static case. Because that's a static potential. That's like electrostatics. But now we are in gravity. When we want the potential between that attracts or repulses two bodies, two masses, we are in the static case. That means no time dependence. That means that the derivative with respect to time is 0. That means that the energy of the exchanged gravitons is 0. Gravitons, photons in the electrostatic case. So if you want to compute the potential, here p squared will have p0 equal to 0. Otherwise, you have retarded the effect of a retarded potential or an advanced potential, depending on whatever it is, your case. But here it is static. So you assume that the two bodies have been there forever and they will stay there forever. And you are asking yourself how much they attract or repulse or themselves. Next, we want these stress tensors to be conserved. that means that if you contract it with this p mu, you have to have 0. And what is this p, this derivative? That is again the momentum p that is exchanged. Because in a momentum space, this is a box, these are derivatives, and they act to the left. And if you want, you can reverse them and make them act to the right. So the momentum, let's see the case of mass m. So far, P0 equals 0 means that you have a momentum of this form. The form momentum is 0p. But in the case of a mass m, that's sufficient to have transversality, because you just have T00, 0, so P mu T mu nu is, there is only T00, 0, so that would be T00 P0, that is 0. So that is already conserved. In the case of radiation, instead, you want P mu T mu nu equals 0, and that is equal to E P mu U mu U nu. So you want that these four vectors are orthogonal, and that means that since P0, since U mu has only components 0 and 3, that just means that P space P should have no component 3. So that's sufficient to choose a 4 vector with 2 components x and y and no components along 3. Well, that's obvious, because if you have a mass and if you have light, and light has this direction, the attraction will be orthogonal. So that's what it has to be. So necessarily, with this choice, we are satisfying everything. And then we compute the potential between two masses, M1 and M2. Two point-like massive objects. And M2. And what's that? That is this thing, where we need to compute this with two, so the first vertex, propagator, second vertex. First vertex is minus ik stress tensor of the first object, minus I kappa stress tensor of, let's say, M1. Then you have the propagator, which is written here. I divided by 2p squared, and let me replace p squared by minus, there is no p0, so minus space p squared, and then there is eta mu rho, eta nu sigma, plus eta mu sigma, eta nu rho, minus eta mu nu, eta rho sigma. And then there is the second stress tensor for the mass, let's say M2. Let's see what happens. So minus I and this minus cancel out, and we remain with I divided by 2 space p squared. T mu nu m1, we know that it has only the component T0, 0, and it is equal to the mass. So we just have the mass m1, we will have the mass m2, and we will just need to compute the component 0, 0, 0, 0 of that matrix. 0, 0, 0, 0 is obviously 1 plus 1 minus 1. 1. So that is the result. In Fourier transform, you get the potential. Because the Fourier transform of this 1 divided by space p squared is 1 divided by 4 pi, 1 divided by r, 1 over r. I forgot k squared. Okay. That is the potential. Now, that should be k squared m1 m2 divided by p squared should be equal to the Newton constant. There is a normalization, a convention, but let's fix one and we will use it always. So Newton constant. So we take out the I and the 2. The I is, of course, to be taken out. And that means that the Newton constant is equal to k squared. Because we want this law. 1 over r with certain constant that at some point we will call Newton constant. Now we ask ourselves what changes when instead of exchanging a massless graviton, the two bodies exchange a massive graviton. The objects a massive graviton so we want to see the difference. And that means that we have to use the Pauli fields propagator for the massive graviton that we saw the other time, or one of the last times. So you have 1 over 2, 1 divided by p squared minus m squared, let's say mg squared, the mass of the graviton. And then we had a similar structure p mu rho p nu sigma plus, but with pi's and a different coefficient. That is the crucial thing, pi mu sigma minus 2/3 pi mu nu pi rho sigma. And what was this pi? Pi mu nu was equal to eta mu nu minus p nu over m squared. So now if you want to exchange that thing, you have to repeat the same calculation and compute the 0, 0, 0, 0 component. That's not difficult because in this pi you can throw away the second part because the stress tensors are conserved. So every time you have a p mu, it will p rho, p sigma, it will contract with this, p mu will contract with that, and since the stress tensors are conserved, basically we can ignore that. And it's like having etas, so you need to compute the 0, 0, 0, 0 component, which will be 1 plus 1 minus 2/3. So let's see. If you exchange a massive graviton you have now for the massive graviton we will have to assume a similar interaction, J mu A mu will be similar, but the constant will be a priori different. So let's call it Km or Kg, kappa G. And the only thing we know experimentally is the Newton constant. So we have to find a relation between the Newton constant and this kappa we have introduced. In the first case, massive graviton, we found it. And then we can use it for the rest. In this case, we have to find it now. And so you have minus IKG T M1 mu nu. Then you have this propagator where P0 is again equal to 0. So I can write minus P squared, space squared. And then I have the 0, 0, 0, 0 component of that, which is 1 plus 1 minus 2/3. So that will be T0, 0 minus I kappa G T0, 0 M2. And this is just M1 and M2. So again, you find there was a 2. There was a 2 to divide. I divided by 2 kappa G squared M1 M2 divided by space P squared plus mg squared times 1 plus 1 minus 2/3, and that is 4/3. And again, this thing should be equal to G m1 m2 divided by space p squared. Perhaps I forgot space p squared, space, because that is equal to 1 over r. Now in coordinate space, you get the right potential. The mass of the graviton that makes it a Yukawa potential, so if you compute but we assume that the mass of the graviton is very small, so basically this we can neglect, and we will not notice the difference between the massive graviton or not at this level, because we can always identify G as 4/3 kappa G squared. So that's really too difficult to detect with the Newton potential. And in this respect, you should know that the Newton law has been tested only down to 1/10 of a millimeter. Below 1/10 of a millimeter, we have no idea if the Newton law is still valid or modified, experimentally, I mean. And that's not a small distance. It's just 1/10 of a millimeter. You can see it. You can imagine how difficult it is to make these experiments, to test the gravitational force, because there are so many disturbing effects that you have to take care of. Okay, so at this level, we do not see any difference between a massive graviton and a massless graviton, because it is always possible to match the constants with the Newton constant to get the right formula, and everything else works apart from the constant in front, because it's, you see, proportional to the potential is proportional to the masses, and the force is inversely proportional to the square of the distance. There's nothing else you can do. Now we repeat the calculation for the deflection of light, both by means of gravitons and by means of massive gravitons, and there we will see the difference, because now we have already determined the values of G and the coefficients. The deflection of light means that you have to compute these two things, but in one case you will have a mass. In both cases, actually, you have a mass, m1, m1, and a photon, energy. So this is a body and a photon, m1, E. And we want to compare the two. So m1, E. What is it? This is minus I kappa T mu nu of our mass. So let me call it UM, that is the stress tensor. Then you have its propagator. Let me already use the fact that we are in the static case, and the propagator is this. And then you have minus I kappa, and instead of having the another mass, you just have E rho u sigma, where this is a photon. And here you see that there is a difference. There is a difference because the photon is traceless. This is traceless, and so the trace part goes away. And as far as the mass is concerned, you can only have 0, 0 there. But if you have 0, 0 there, it means that you need to have 0, 0 in the other sector too. So again, you end up with the component 0, 0, 0, 0. So you have kappa squared I 2 space p squared m1 energy, and now you have a factor 2, 1 plus 1 there, 2. And in terms of the Newton constant, since kappa squared is the Newton constant, we can write it like I G m1 E space p squared, because the Newton constant is kappa squared. Now we repeat the calculation with the massive graviton. Essentially have the same formulas, but kappa m and the propagator is different because there is a mass which will be negligible, so that is actually not the real deal. I write it and I cancel it at the same time. The difference is that you have these pi's. Pi mu rho, pi nu sigma, plus pi nu rho, pi mu sigma, minus pi mu nu, pi rho sigma. And that multiplies minus I kappa m E u rho u sigma. Again, we can simplify this a lot because the stress tensors are transverse, so every pi reduces to eta. Because remember that pi mu nu is eta minus impulses, momenta, which will get contracted with either of the two stress tensors, and in any case it will give 0. But again, this will remain equal to eta mu nu eta rho sigma, which contracts, which traces the stress tensor of the photon and gives 0, which means that again this will give 0. And as far as the rest is concerned, is the same as before, 0, 0, 0, 0 component, because this is 0, 0. And so you will get again 1 plus 1. Here it doesn't seem to be very different. So you have 1 divided by 2 space p squared kappa m squared m1 e times 2. And now we know that kg, not km, kg, kappa g. And we know that kappa g squared is 3/4 Newton constant. And this is the discontinuity. So now we have determined what the Newton constant is by means of a different experiment. The two things are fixed, and you find that the effects of the deflection of light is reduced by a factor 3/4, even if the mass of the graviton is arbitrarily small. So that is why it is called a discontinuity, because the two things are different. And the difference is that if you exchange a graviton, you exchange only 2 helicities. If you exchange a massive graviton, you exchange 5. So it's totally different force, no matter how small the mass of the graviton is. And needless to say, the experiments are in agreement with the massless graviton. So that's a very powerful check, because it does not depend on it does depend on the mass. If the mass were large, it would depend on the mass of the graviton, but as in the limit when the mass goes to 0, it doesn't, and it is different by a finite amount from the result you get from a massless graviton.